Hello, this is Math2231 coming to you from the College of DuPage during the summer of 2020. And this lecture is the conclusion of the lecture. When last I left you, you were working on this problem. I hope you finished it, but perhaps you didn't. In that case, you know what to do. And now let's see how you did. This first example has 4 to the w minus 5 logarithm base 9 to the w. Again, the base here is 4, the base here is 9, so that means we have constants. So the r prime of w is equal to 4w times the natural logarithm of 4, like we learned before, minus the 5 just sits there, but then this is going to be 1 over w times the logarithm 9, and that is the logarithm base e of 9. On this one, what happens, we have two terms. The second one, however, is a product. So when we take the derivative, we're going to get 3e to the x plus, and then we do the product rule. So it's the derivative of the first, 30x squared, times the ln x, plus the first, 10x cubed, times the derivative of the second, which is 1 over x. We simplify that and get this expression. This last one is the quotient rule. So it's going to be the denominator times derivative of the numerator minus, this is the numerator, times the derivative of the denominator. The derivative of 1, of course, is 0. And it's all divided by the denominator whole squared. Now when you simplify this, you see this term will cancel with this term. And so your answer simplifies to this. Again, algebra is your friend. And I will usually ask you to substitute in numbers. Just like sometimes doing algebra before calculus helped us in the past, we find that sometimes doing properties of logarithms before doing the calculus will help as well. Here is an example. And certainly we could do this just using the chain rule. But let's see if we can use properties of logarithms to maybe make this even simpler. You know what to do. Let's see how you did. Well, you see the logarithm of x plus 1 whole to the 1/2 is the same thing as putting the 1/2 in front times the ln of x plus 1. So now when we take the derivative, well, this was just doing properties of logarithms pre-calculus, the 1/2 will just sit there, but then I'm taking the derivative of the natural logarithm of x plus 1. So that is going to be 1/2, and then the derivative of ln of x plus 1 is 1 over x plus 1. Notice that those parentheses are important, and this is the answer that you get. You would get the same answer if you were using just the chain rule without the properties, but it would be a much more complicated simplification. Here's one for you to try, and again, it's quite involved if you were to take the derivative using the chain rule, but let's use properties of logarithms and see how it helps. You know what to do. Let's see. Okay, well, this is just algebra, but the logarithm of the quotients is the difference of the logs. But in the numerator, you have a product. So the logarithm of the product is the sum of the logs. And you also have this factor, x squared plus 1 raised to the second power, so that 2 is going to come in front. So you see this is going to be the same thing as the ln of, and we will talk about the numerator, so that's the ln of x plus, this is going to be 2 times the natural logarithm of x squared plus 1 minus, and this is the denominator, but you see I handle the square root by saying the denominator is 2x cubed minus 1 whole to the 1/2, so the 1/2 can come in front, and this is the logarithm of 2x cubed minus 1. Now you see this was just using properties of logarithms, nothing other than that. But now we'll do calculus, so we take the derivative. So f prime now is equal to the derivative of this is 1 over x. The 2 just sits there. Now I have to use the chain rule. So the 2 sits there. The derivative of this is going to be 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x. That's what we get for that term. And here we have minus, the 1/2 just sits there, but it's the derivative of the ln of 2x cubed minus 1. That is 1 over 2x cubed minus 1 times the derivative of what's inside, which is 6x squared. We can simplify this a little bit. Algebra is our friend, and we get this expression. Again, realize often I am going to ask you to plug numbers into these answers. On occasion, it is convenient to use logarithms as aids in differentiating non-logarithmic functions. And this procedure is called logarithmic differentiation. This is one of your learning objectives. So let's talk about an example where we want to find the derivative of this function right here. So you see, what I'm going to do is, and this would be pretty complicated because I have a complicated denominator, a complicated numerator, and it would be quite a bit of work. But what I can do is I can say, oh, let's look at the natural logarithm of y. This is what y was. We'll look at the natural logarithm of y. And the natural logarithm of y is equal to the ln of this. Now, by the way, x can't be 2 because 0 is not in the domain of the logarithm. So here I just took the logarithm, but now I'm going to use the properties of logarithms. Again, this is going to be the logarithm of the numerator minus the logarithm of the denominator, but then I'm going to use those power properties, bringing these constants inside. So you see the ln of y is going to be 2, the natural logarithm of x minus 2, minus the 1/2 can go in front, natural logarithm of x squared plus 1. Those are just logarithmic properties. But now I'm going to take this expression and take the derivative, but I'm going to be using implicit differentiation. So you see here, this is going to be 1 over y times y prime. And here is going to be the 2 just sits there. This is 1 over x minus 2 minus the 1/2 just sits there. And this is going to be 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x. So I get this expression. Now what I can do is I can, and I can simplify that a bit, which is what happens here with common denominators. So I have y prime over y is equal to this business, but now what I can do is multiply both sides by y. So y prime is equal to y times all of this expression. But y, going back to the beginning of the problem, was this. So I can put that expression there in front, and I can simplify, and I get this. Now, even though I talked for this a very long time, it actually didn't take me very long to do this at all. And this is an easier expression to substitute numbers in than what I would have had taking the derivative of this straight up. Logarithmic differentiation. Because the natural logarithm is undefined for negative numbers, we will often encounter expressions of the form the natural logarithm of absolute value of u. And this theorem says that you can take the derivative of this as if the absolute value function was not there. So what it says is if u is a differentiable function of x and u does not equal to 0, then the derivative of the natural logarithm of the absolute value of u is equal to u prime over u. Normally I don't look at proofs, but I'll look at this one. If u is bigger than 0, then the result follows from our standard result. But if u is less than 0, we know that the absolute value is equal to minus u. So the derivative dy dx, or d dx rather, of the natural logarithm of the absolute value of u is the derivative with respect to x of the ln, and now this is minus u. So this is going to be 1 over minus u times the derivative of that, which is minus u prime. And you see the negatives cancel out, and I get the result that I want. Here's a problem for you to consider. Find this derivative. You know what to do. Let's see how you did. And it's just going to be the derivative of the cosine is minus sine of x, and this is going to be cosine of x, and that is going to be simplified as negative tangent of x. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless y'all.